Okay, in this segment, I'm going to show another type of find based off of binary search trees that's relevant to geometric problems, in particular problems such as the Barnes-Hut algorithm, where we're interested in finding overlapping intervals. So this can be useful, for example, if you want to find regions, rectangles that overlap in some discretization of a space. Or it actually came up last quarter when we were looking to find intervals that people spent time in common that were coming and leaving from an area that they visited randomly according to an exponential distribution and for a particular period of time. And it can be tricky, and this is a nifty algorithm based off of things we know already, that I can do this in log n time. So I don't have any prepared notes for this, so let me share my iPad screen. So the functionality supported by the interval search is listed here in the top left of the screen. We want to be able to insert an interval into a set of intervals. We want to be able to remove an interval. We want to ask if an interval exists, but most importantly, the one that I squared off, we want to look for an intersecting interval. And that is the most difficult and the most interesting part of this data structure. So on the right, I list some simplifying assumptions to this implementation just to make the code very simple. Neither of these is challenging to overcome at all. I'll say how to overcome them actually. The first is that the left bounds of the intervals are unique. So whatever the intervals are, you're not going to have two with the same left boundary. It's very easy if you do to just add something to the code that merges intervals, that spots that case. So that's not a problem, just adds a couple lines of code. The second is that we're just looking for any intersecting interval, not all of them. If we want to do all of them, we can just run the algorithm as many times until we don't find any more. So that's not limiting, it's just a little bit easier to present. Okay. And what do I mean? And what do these intervals look like? Well, they're just intervals. I draw integers here, but they don't have to be integers. And so I have an example set of intervals, 17, 19, 5, 8, 21, 24, and so forth. And I might create a set of those intervals, and then I might want to add a new interval, and then I might want to ask for some other interval, does this interval intersect any of the intervals that I have? Okay. And so first thing we'll do is talk about what the data structure looks like to do that efficiently. So the data structure is interesting to us because it's something we know already. It's a regular binary search tree, but it's keyed just by the left bound. Okay, so we're going to populate, we're going to insert, we're going to populate the set with new keys by doing a regular BST insertion based off of the left bound as the key. Okay, we're going to have one other piece of information that we don't typically have, and that is going to be at each node, we're going to store the maximum bound in its subtree. So in other words, starting at whatever node you're interested or whatever node, pick any node, start there and look in all the nodes in its subtree and find the largest value, the largest bound of any interval in that subtree and store that and do that for every node. Okay, so I draw that, as you can see at the bottom here, just next to the node interval. So imagine then that we wanted to build one of these data structures with the first, say, 6 of the keys that I have listed in the example, and then I'll add the 7th, and we'll go through the add process together. But if we built the first 6, it would look just like this. Okay, so we see that a regular binary search tree, the root is keyed by 17. So just to the left of it, it's keyed by 5. To the left of it's 4. 15 would be to the left of the root, but to the right of the root's left child, and so forth. So we're just doing a regular binary search tree with the left bound as the key. Now, the little number I have just to the right of the node intervals are the maximum value of any interval in the subtree. So if you look at the root, for example, notice that if you look at the right subtree, the right bound of the right bound is 24, and there's nothing else in that right subtree. So that's the maximum. If you go left, for example, the node 5, 8, this node right here has, if you look at all of the intervals in its subtree, the highest value of any bound is 18 in its right subtree. And similarly, if we look at that node, it happens to have the highest bound in any of its subtrees. And you see this is very easy. So anytime that we're going to insert a new interval, we're going to have to potentially update that value along the search path of where to insert that interval. So if we just keep a record of the search path, of where to search that interval, we can just go back and, if necessary, adjust the values of the maximum key in the subtree for each of those nodes. So we store one extra piece of information, and that's going to be the key to making the algorithm very, very simple. All right, so then let's do an insertion of the last element. The last element is 1622. Okay, so I'm going to insert this. I'll just put it here for simplicity. We're going to insert 1622. Okay, and we're going to do it just like a regular BST. So it's less than 17, it's greater than 5, it's greater than 15. So it's going to be a leaf. We're going to put in 1622 here. Okay, and we have to retrace the search path. So we have a record of the search path. It's easy to code. And going back through that search path, we have to ask, would that 18 change? Well, yes. So what we do is we find the highest value of the key that of the interval we just inserted, and then we go back and ask, is that higher than anything that was already, than the value that was already stored for that particular node? And the answer is yes, yes. And when we trace all the way back and get to the root, the answer is, well, no, not here. So leave that alone. Okay, so after insertion, our search tree looks like this. So it's almost exactly the same as a regular BS tree insertion. We could do rotations. In this case, I'm not going to do rotations. We'll just assume the tree stays reasonably balanced. But either way, it's a very simple algorithm. Now it gets a little trickier. It's a little hard to understand why this works. So you'll have to think about it a little bit. But I'll present the algorithm for the last part, which is the interesting part, which is to find an intersecting interval. Okay, so we'll take some intervals and we'll go through the algorithm and see that it works, and then maybe think a little bit about why it works. And now I'm going to show the code for finding an intersecting interval. And I'm going to use the same tree that we just developed last time. So I copied it over to a new page. I updated the max value for every subtree. You see it's 22 there after my insertion of 1622. And I'm going to just go through the following 4 cases, and this will always work. This will find an intersecting interval. And once we find one, if we just do a lazy delete of it, for example, we do the algorithm again, we can find another one until we're out of them. So I'll just show you how to find one. And I'm going to call the interval bounds low and high, as you see to the right here, just because I use it in the high-level code description below. So the algorithm is going to look like the following. If I'm going to start with the root node, and if the interval intersects, so this assumes that you can calculate whether the left bound or the right bound lie between the left and right bounds of the interval you're comparing it to. So you have a simple little macro to determine if one interval intersects another. Okay, so if it intersects, return it, you're done. Otherwise, if the left child is null, then go right. Otherwise, look at the max endpoint in the left subtree. That's this little number that we have next to the node intervals that I talked about. So if the max endpoint in the left subtree is less than low, then you know you're not going to find anything in the left subtree, so just go right. Otherwise, you might find something in the left subtree, so go left. Okay? Again, this will always find a interval that that intersects, but it won't find all of them the first time through. Okay, so let's just do some examples. We will use the same tree that I have here, and we're going to say this first one, insert 2325. So what do? We start at the root. Does 2325 intersect 1719? No. Okay, so is 22 less than the left bound of the interval we're searching, 23? Yes, it is. So the third condition there says there's not going to be anything to the left. It's impossible. And I think you can see why now, right? Because 22 is as big as anything's going to get in the left subtree, and our low bound is 23. So if there's anything here, it's got to be to the right. So we're going to go down the right tree here. Okay, and does 2325? Yes, it does. So we would return right here that particular node and we found an intersection. Okay, so that's a simple case where we just had to traverse one node to the right. So now let's look at another one, insert 1214. This will take a few more steps. Does 1214 intersect the root? No. Is 22 less than 12? No, it's not. So we're going to have to descend the left subtree, okay, because there could be something there. Does 5, 8 intersect 12, 14? No, it does not. Does the left subtree have any potential? No, it doesn't, because 8 is less than 12. So forget about the left subtree, and we're going to go right. That's what the algorithm says. If you don't go left, go right. So when we go right, does 12, 14 intersect 15, 18? No. Does the left subtree have any potential? No, because 10 is less than 12. So if you don't go left, go right. We're going to go right. 16, 22 does not intersect. And of course, left is null. And that is condition 2. If left child is null, go right. And so we're going to go right, and it's null, so we're done. Okay, so this is not in the tree. I mean, there's nothing in the tree that I should not have put insert. I made a little mistake here. Sorry about that. These are search operations. I think you knew that from the context, but I'll correct it here. So when I say search, I don't mean search for the interval, I mean search for overlaps. I say it above, but just to clarify. Okay, so this is not going to be, there's not going to be any overlapping interval in the tree. And now we're going to search for any overlapping intervals for 21, 23. And let's see how this goes. So you might notice that there are two different possibilities in here. And actually, since I assume the left intervals wouldn't match, why don't I just say 20 to 23? 1 second here. Yeah, we'll make this 20 to 23. Simplify it a little bit. All right, so what would this look like? This would look like root no. Do I go left? Yes, because there's still potential because 22 is greater than 20. Do I go left from this node here? No, I don't, because 8's too small. Go right. Is 15 through 18 match? No, it doesn't. No point in going left. Do I go right? Yes, I do. Does that match? Yes, it does. 20 to 23 overlaps 16 to 22. So I return this node here. Okay. I notice I have another node here. So if I get rid of that node, I change 22 to the proper numbers, which look like they would be 18 and so forth. So if I adjust all of these, right, that would be 18. This would be 18. Okay. Then when I started, and that stays 24, when I start the algorithm, there would be no point in going left, right? So I'd go right, and then I'd find this one the next time. Okay. So hopefully that gives you an intuition of how it works. If the search tree stays balanced, it's log n. It's incredibly simple, great application of a regular binary search tree to a problem that is relevant to things we've done this quarter and things that have come up recently in other classes. You find it in a lot of different places.